All right, here we are at our 8.5 notes continued. Here we're just looking at the volume of a cone. And as we look for a cone, we notice that, again, it kind of follows that trend for volume base times height. Now, as we look at our shape, looking at our base, we see that, again, we're kind of just working with that circle. So that would represent our base. And the area for that circle is, again, pi r squared, much like the cylinder. And then times height. Now, really the only new difference on like a cylinder versus a cone is we pretty much do exactly what we were doing before, but then we just multiply it by this coefficient of 1/3 or divide by 3. And so when I tell my students, I'm like, yeah, that's all. They're like, wait, Mr. B, that's literally it? I'm like, yeah, that's all there is extra. And they're like, oh, okay. So as we do these, it should be pretty similar to what you just saw, and then just multiply it by 1/3 in the end. So here's our cylinder, and notice on this example one, they give us the diameter. So as a result, we do need to find the radius, and our radius is actually 2. Our height we know is 6, and so we can go ahead then and plug this in the volume formula for a cone, which is 1/3 base times height, or in this case, 1/3 pi r squared times height. And so we go ahead and we plug these items in. We have b equals 1/3 times pi times our radius is 2 squared times our height is 6. And so we end up with v equals 1/3 pi times 2 squared is 4 times 6. Next, we're going to go ahead and multiply our two values here together. So there we would get 24. And then 1/3 of 24 comes out to be 8 pi. So this is our exact value. And then in terms of a decimal, that would come out to be 21 or 25.1. And since this is meters, we have meters cubed. So these are our two answers. So really, again, just like the cylinder, and you take 1/3 of that. My students are like, literally, that's it? And I'm like, yeah, that's it. So go ahead. Please feel free to pause the video if you have any questions at all. But if you're good, go ahead then. Please pause the video and try example 1 from the You Try It. All right, so as we look at this one, we have our radius is 6, our height is 15, and our volume equation for a cone is 1/3 pi r squared times height. And now we go ahead and plug our values in. So we have 1/3 times pi times our radius is 6 squared times our height is 15. Cleaning this up, we have 1/3 times pi, 6 squared is 36 times 15. And as a result, when we multiply these two values together, we end up with 540. And then 1/3 of the 540 gives us 180 pi, which as a decimal would come out to be 565.5. So this is centimeters cubed. Now, I've had students ask me in the past, hey, Mr. B, since we use pi, right, to get the approximate value, technically, like to the letter, this would be about, okay? But from my experience, most teachers, because you're working with pi, and it's assumed that because it goes on forever, that it's going to give you a approximate value anyway. I know I am, and I know a lot of teachers are okay with the equal sign there, even though in reality, technically, yes, it is an approximation. Okay. If you do the approximate value, you're always going to be covered with those squiggle equal signs. But I know I'm generally okay with the equals because, again, it's pretty much that value as the decimal. Go ahead, feel free to pause the video if you have any questions at all. All right, now looking at example 2, on this one, it's a lot like the cylinder types where we were trying to find a missing variable. Now for this, we have a missing height, but we are given the radius, and our volume is given as well, 956. We know our volume equation is 1/3 pi r squared times the height. And what we can go ahead and do is plug in then our knowns. So we have our volume, which is 956, equals 1/3 pi times our radius is 9 squared times our height is, we don't know. So that's actually what we're trying to figure out. Now, what I encourage students to generally do is, a lot of people kind of jump to this 9 squared and then kind of take 1/3 of that and so on. Like I've literally had students describe their process, and that's that. It is that. And that's not bad. Like that's absolutely correct. Now, there is kind of, I would say, a safer path to take. And I'm going to say why here in a second. But what I would encourage students to do is see that 1/3, we're going to multiply both sides by 3. Okay, essentially, guys, we're going to be clearing this fraction out because we don't like fractions, right? And so 956 times 3 gives us 2,868 on that left side. Now, on the right side, this 3 is going to cancel with the 1/3. And so we're just left then with the pi times the 9 squared times the height, right? Okay, great. Well, we don't have any more fractions, right? And so now we can kind of solve like we normally would. So here we have 2,868 equals 81 pi h. And then naturally you would just pretty much divide this 81 pi over. 81 cancels, pi cancels, leaving you just your h equals 11.3 feet. Okay. Now, a lot of students, though, or not a lot, but some people may just kind of want to try working on this right side. And that worked out for the student who described his process. Now, the only downside, though, with that is 9 happens to be a multiple of that 1/3. And so there it would have conveniently worked out to where you kind of get clean numbers. But by and large, you're not going to have like a radius or a height, even if you're trying to solve for the radius, where it is a multiple of 3 like that. So for example, if our radius was like 4, let's say, and then I did 4 squared is 16, and then I try and multiply that by the 1/3 part, well, then I'm ending up with this fraction, aren't I? And so as a result, generally speaking, I highly encourage students to kind of just, hey, let's clear the fraction out. Let's get rid of that 1/3 by just multiplying both sides by 3. Okay. And so that'll even kind of transition or transfer over to when we get to the spheres too, when we're trying to solve for like a radius. So it's just kind of like, that's how I personally would approach it, just because it kind of checks off other areas when numbers aren't as clean. All right. So go ahead, feel free to pause the video if you have any questions on example 2. All right, go ahead. For the you try it, give this guy a shot. Looks like, again, we're looking for another height. We have the volume and the radius given. Go ahead and try example 2, or the you try it 2. All right, and there we have our example 2 on the you try it. So we should have ended up with 30.6 yards for that height. Go ahead, feel free to pause the video if you have any questions on it. All right, now as we move on to example 3, example 3 is asking for The inside of a glass is shaped like a cone, which glass can hold more liquid. And so essentially, guys, what we're doing here is we're finding two different volumes. They are cones, and then we're just going to compare the two. So I'll go ahead and do the first one, and then I'll let you guys do the second one. So I'll do glass A. So we have the volume is equal to pi r squared, 1/3 pi r squared times the height. Our radius is 4, our height is 8. And then we go ahead and plug these values in. So we have 1/3 pi times our radius is 4 squared times our height is 8. And so our volume is coming out to be 1/3 pi times 16 times our 8. And as a result, we end up with 1/3 times pi times 128. And unfortunately, 3 doesn't go into 128 evenly, so we're just going to have 128 over 3 pi as our exact value. And then when we multiply that by pi, we end up with v equals 134. Should be to the nearest tenth, I believe, but we'll just do 100th, 0.04. And we are centimeters, so centimeters cubed. Okay, so there is cone A in that glass A. So go ahead and try and find B with that radius and that height. All right, so as we look at glass B, that's in the red here, we do notice that we ended up with 30 pi as our exact value and 94.25. So the bigger of the two is glass A. Okay. Go ahead and feel free to pause the video if you have any questions at all. All right, moving on to example 4. You have 10 gallons of lemonade to sell. 1 gallon is 3,785 centimeters cubed. Each customer uses 1 paper cup. And how many paper cups will you need? All right, so as we look at example 4A, what we need to keep in mind is these are those paper cups that are kind of in those, like if you get like at a water cooler where they kind of have that cone shape. And so this is, again, those like really small paper cups. And so let's go ahead and first start off by figuring out how many, like what's the volume based upon how many gallons we have. So we know that 1 gallon holds 3,785, 3,000. So 3,785 cubic centimeters. Now we have 10 of those, 10 gallons. And so as a result, we essentially just have 37,850. Just kind of add on a 0, right? Now, how many paper cups will we need? And it's not in the question, so I do apologize, but our dimensions for our cone are 8 centimeters across as a diameter, and the height of this would be 11 centimeters. So what we need to go ahead and do is find the volume of this. And so our volume, again, is 1/3 pi r squared times the height. And so we can now go ahead and plug in our values. So the volume is equal to 1/3 pi. Our radius is actually 4 here because our diameter is 8. So 4 squared times our height is 11. And as a result, we'll zoom in so we can see it a little bit better. We have V equals 1/3 pi times 16 times 11. In which case we end up with V equals 1/3 pi times 176. And as a result, our exact value comes out to be 1/3, oops, not 1/3, 176 over 3 pi. Unfortunately, I couldn't go into it evenly. And as a decimal value, this would come out to be 184.3. So this is how much cubic centimeters that there are. Okay, so we found how much volume each one of these little water cups can hold. And now we've got these gallons, right? Like how many paper cups would you actually need then? So what we're going to do is we're going to take our 37,850, 37,850, and we're going to divide it by how many, what the volume is for each one. So I'm not going to actually do it by longhand, but you could. This I would just pretty much use a calculator for. So 184.3. And when we do that, we end up with about 205.3. So you would need about 205 cups to essentially have those 10 gallons of lemonade. Okay. Now for B, it's asking for the cups are sold in packages of 50. How many packages would you need to buy? Well, this is then where you would take your 205 cups that you have, 0.3, and then divide that by 50 because they come in packages of 50. And so you can't have 4, you just wouldn't have enough. So you would need 5 packages. Okay. Finally, how many cups would be left over if you sold 80% of the lemonade? Well, we know how many gallons we have of this lemonade. It's 37,850. And we're selling 80% of that. So we could just multiply this by 0.8. And when we do that in the calculator, we get 30,200. 280. And that's how much you would use, right? Well, if you were to take then 37,850, subtract the 30,250, I'm sorry, 280, you're then left with 7,570 in terms of the volume left over, so cubic centimeters. And we know that each cup holds a total of 184.3. So we can take again, this is the leftover, the 7570. And each one of those cups holds 184.3. And so when we divide these, we end up with 41.07 cups. That's how many cups would be left over. 41.07. So again, we had to kind of figure out, well, what's 80% of that? We found that value. And then we subtracted it from our total to kind of get like what was left over that we didn't quite sell. And then knowing that value, we could then divide it by however many, like the volume for each cup, those cone cups, to then figure out, well, how many are there then? And we got 41.07. Go ahead, feel free to pause the video if you have any questions at all.